Welcome back. You came back to learn more, and that's great. Okay. In this video, we are going to talk about an overview of binary storage. Okay, the data storage units, their calculations, and an overview of their uses. Okay, so let's start. So overall, okay, we know that computer works in binary, and we have just gotten bits in processors or RAM. Okay, bit. Okay, we know what bit is. Bit is a binary digit, the absolute smallest unit of digital data. A processor contains billions of transistors acting as microscopic switches with only two states, on and off. And one of them is just known as a bit that can store only 1 0 or 1 1. Then we have gotten the nibble. The nibble, it means 4 bits. 4 bits makes a nibble, okay? And it was used in the older system versions to represent one hexadecimal value. And after that, we have gotten the byte. Okay, byte is 8 bits. 8 bits is called 1 byte. Okay, so where it's used, okay, that is just the fundamental building block of modern data storage. Every character of text, pixel of color, and note of sound is ultimately constructed from bytes, maybe 1 byte, 2 bytes, 3 bytes. So we have the data sizes or the register sizes that we have, they are just based on this 8, okay, whether that is 8, 16, 32, or things like that. Okay, so there are some bytes. That's why byte is very important. Then information capacity and the 2 to the power of n engine. So we have discussed before as well that the number of unique binary patterns generated by n bits is always exactly 2 to the power of n. For example, if you have gotten only 1 bit, you can store two different things there, okay? 1 1 or 1 0. If you have gotten 2 bits, in 2 bits we can store 4 different combinations of ones and zeros, okay? 0 0 0 1 1 0 or 1 1. If you have gotten 8 bits, which is 1 byte, how many different values can you store in a byte? That is 2 to the power of 8, which is 256 distinct combinations. What if that is 16 bits? In 16 bits, you can store 2 to the power of 16. There is a typo, which is equal to 65,536 distinct combinations. And as you can just increase that, you will just have different, more and more number of distinct combinations possible here, okay? You have to remember one thing, the wider the range of values or variables required, the more bits you must allocate for a value, and every single additional bit doubles the number of possible combinations. See here, if we have gotten 1 bit, we can store 2 different values there. If we have gotten 2 bits, 2 doubled, that will be 4, so we have 4 combinations. If I make it 3 bits, so 2 to the power of 3 is 8, that doubles, okay? 2 to the power of 4 is 16, that doubles. So every bit that you add to the register or to the number of bits, it doubles the number of possible combinations. And as we have studied in the previous videos, the universal translator, okay, so representing media, all kind of media stored in computer has to be changed to binary, okay? And we have just studied how to do that. For example, the first one, text or characters, okay? So we used character sets to change text or characters to ASCII code, okay? In which we studied ASCII that uses 7 bits, and we have gotten 128 different characters there. And now mostly just we use Unicode that is a multi-byte system encoding, okay? And in which we can just have millions of global characters. So Unicode can just use 16 or 32 bits. The next one, images, okay? Images are made up of pixels, and color depth is the number of bits used to represent the color of a single pixel. So if you are using 8 bits as a color depth, it means you can just show 256 different colors, okay? And continuing like that. Sound waves, okay? Analog sound is captured as digital snapshots at different times, okay? Which is sampling. And sample resolution or bit depth is the bits per sample. A 16-bit resolution allows 65,536 different audio volume levels, okay, which is again 2 to the power of 16. And the last one, instructions or code, program codes, okay. Program code and software instructions are also stored as strict binary sequences that are fetched and executed directly by the CPU. So everything is changed to binary in computer. The other thing that we have gotten, okay, mostly students make mistakes in, that is the prefixes, okay, kilo and kibi. What is the difference between them, okay? So kilo is of base 10, kb is just the base 2, okay? So remember that. In 1998, the IEC created a standard to fix the confusion between storage manufacturer labels and actual computer processing. See the decimal system, which is just base 10, okay? Multiples of 10. For example, we have gotten kilobytes, megabytes, gigabytes, okay? KBs, MBs, and GBs. They are just 1,000. For example, 1,000 bytes make 1 kilobyte, 1,000 kilobytes make 1 megabytes, and 1,000 megabytes makes 1 gigabyte, okay? On the other hand, the binary system, there is multiples of 1024. For example, 1024 bytes makes 1 kibibytes. 1024 kibibytes makes 1 mebibytes. 1024 mebibytes makes 1 gigabytes. So where they are used, okay, decimal system is often used by hardware manufacturers to make storage drive capacities appear larger. For example, when they are just telling you 10 GBs, 10 GBs, that is just actually calculated like this, okay, with 1,000. While Gibibytes is just more, okay, that is just more than that. That's why when you just buy storage devices, for example, flashes or SSDs, on them it is written, for example, 500 GBs. But when you just open it inside the computer, that shows somehow less than that, okay? Because this decimal system is used for making the capacities appear larger, while in reality computer uses the binary system, okay? So usage of binary system that is used by computer processors, operating systems, and required by the IGCSE standard. So mostly you will use this one unless directly you are told to just count it in kilobytes, megabytes, or things like that, okay? And the storage hierarchy, again the same thing, okay? 8 bits makes 1 byte, 124 bytes makes 1 kibibytes. So in all of them we have gotten 124, okay, 1024, okay? 1024 kibibytes makes 1 mebibytes. Then again just gibibytes, okay? Tebibytes, pebibytes, and xbibytes, okay? So we have gotten that. That is just the hierarchy. So we always just use what? 2 to the power of 10, okay? That is 1024. And the conversion, we know that changing from a smaller unit to the larger unit, we have to perform division, okay? See, from bit to byte, from byte to kibibyte, mebibyte, or just things like that, we have to perform division. We have to divide by these numbers, yeah? But from larger to smaller units, we just multiply, okay? For example, 1 TB is equal to 1, or just the number of TB bytes, that is multiplied by 1024 to just get the GB. That's it. And real world scale and capacity, the IBM 650, which was just created in 1950s, its capacity was 2 kilobytes, 2000 bytes, okay? Barely enough to hold a single page of unformatted text. So today in the smartphones, the photos that you are just capturing with your phones, that is from 3 up to 5 megabytes, okay, which is just a medium resolution image with a standard 24-bit color depth. Then smart TVs and laptop RAMs, okay, the capacity for them is just 4 to 16, or now just many TVs and laptops, they are just coming to 32 or 64 GBs as well, okay. So they are just primary storage, fast volatile working memory accessed directly by the CPU. And high-end SSD capacity can be just in TBs, 4 TBs, 8 TBs, 2 TBs, 1 TBs, okay. So they are secondary storage, can permanently hold roughly 1 million high resolution photos, okay. So there are just some scales in the real world that, yeah, how are they just used. So in exam, you have no calculator. So if you face some questions, you have to just do them by yourself, okay? An image measures 100 by 80 pixels and has 128 colors. So this is not the bit depth, that is just the number of colors. You have to just calculate that, okay? So in exams, you have to be careful about that. Calculate the file size in Kibibytes. So open your notebooks, try to calculate this, then come back to the video to see if your answer is correct, or if not, where you have just made the mistake. See, determine the color depth. So that is 128. So 128 colors requires 7 bits. So that is 2 to the power of 7, which is 128. So the color depth is 7. Then we have gotten calculate total bits. So that is 100 by 80 pixels. That is the number of pixels, and our color depth is 7. So 100 multiplied by 80 multiplied by 7. That is the number of bits. Then convert it to the target unit, which is just Kibibytes. So simple, divide that by 8 and to just make it bytes, and divide by 1024 to reach Kibibytes, okay, where is something like this: 100 multiplied by 80 multiplied by 7 divided by 8 multiplied by 1024, or divided by 8 then again divided by 1024. You can just do that. Now in Edexcel, you can just leave your answer here, you will just get your mark, okay. But if you're just taking Cambridge IGCSE, in that year you will have to just calculate the number. Some knowledge check, some questions, okay, quick recalls. Questions are here. Try to just pause the video after each question and then come back to see if your answer is correct, okay. So how many bits are in a single nibble? That is 4 bits. Good. Order the following from smallest to largest capacities: byte, Gibibytes, Kibibytes, bits, and Mebibytes. So that is bit, then byte, then Kibibyte, Mebibyte, and Gibibyte. What specific mathematical operations moves a value from Mebibytes up to Gibibytes? So think about it. Good. That is just divided by 1024. Just divided by 1024. Okay. So that is from Mebibytes to Gibibytes. Only one division is just needed here. So for your exam, do not forget to show your working, because just the method is marked. Check the final unit. What unit is asked from you in the question. Never use 1000 unless directly you are asked for, okay. Mostly just, yeah, we use the binary multiplier, okay. And okay, paired with leading zeros. Remember, IGCSE uses 8-bit binary registers mostly, okay. So if you are doing any operation and you just get less bits than that, then add some zeros here to just complete the 8 bits, okay. For example, the denary number 11 is this one, okay. 1 plus 2 plus 8, that is 11, and 4 zeros. Not only this, length matters. If you just write this, you might lose marks. That's it for this video. Wish you all the best. I hope your concepts are clear. Okay, if there is any question, I'll be more than happy to answer you in the comment section. Okay, wish you all the best, good luck and goodbye. Do not forget to like and subscribe. See you in the next video.